This is our third experiment. Name of the experiment is heat transfer through pin. Aim to determine the temperature distribution along the given pin, efficiency and effectiveness of the pin under natural convection, under natural conditions. Specifications: diameter of the pipe is 20 mm, that is diameter of the pipe is 20 mm, then the length of the pipe is 120 mm. In this experiment, we are going to determine effectiveness of the pin, efficiency of the pin and temperature distribution along the given length of pin. So this is for these are the some pins for your understanding. Okay, here there are n number of pins are there, but in our laboratory we have considered cylindrical type pin and we are determining the efficiency, effectiveness and temperature distribution for this particular cylindrical pin. This is our experimental setup what we have in our laboratory. First I will name the parts of the experimental setup. First one is the air duct, second is anemometer, third is the induced fan, fourth is the air outlet for free convection, fifth is the temperature indicator, sixth is the voltmeter, seventh is the ammeter, eighth is the heat input, ninth is the air blower switch, 10th is the power switch, 11th is the electrical heater, 12th is the aluminum test specimen arrangement, 13 is the airflow sensor. This is about experimental setup. Okay, so now how to conduct the experiment? You have to switch on the power button, main power button, then you have to switch on the electrical heater, then you have to set the voltage and ammeter reading by rotating this knob. Then after this you have to wait for 30 minutes. You have to wait for 30 minutes so that the pin will get heated. After 30 minutes you just open this opening, then air will flow here naturally and it will come here and it will pass over the surface of the pin. It will absorb some amount of heat and it will come out here now in this particular channel. You can opening, the air will come out here now. This is the working principle now. Then what are the temperature you have to take down here? You have to take 5 temperatures here now. One is T1 air inlet temperature and T2, T3, T4. These are the three thermocouples which are placed over the surface of the aluminum metal pin. Okay, one temperature, that is T1, T2, T3, T4, and you have to take one more temperature, that is T5. T5 is air temperature at outlet. You have to take all 5 temperatures from this temperature indicator by rotating this knob. Okay, after this knob what you have to do? You have to do the calculations. Okay, how to take the reading? Then I will show here. So heat input, as I told you, you can vary the heat input and set the heat input by setting voltage and current here now. What is, we have already set voltage and current, that we have to note down here now, voltage and current. I will explain you one reading. Okay, I have taken 4 readings, then I will explain you one reading, that is 4th reading. Okay, voltage I have set it for 67, current I have set it for 0.77 amperes. Then T1 I got air inlet temperature I got as 35.9 and air outlet temperature, here will be the air outlet temperature I got, that is T5. The T5 is equal to 42.9. Then I got T2 temperature, that T2 temperature is what here? T2, T3, T4. T2, T3, T4, that I have mentioned here now. T2, T3, T4 I got here as T2 as 124.1, T3 as 108.4, T4 as 108.9. These are the readings we have taken from the experimental setup. Once you took the readings, then you have to do the calculations. What is the calculations? You can see here now. I can do only one specimen calculations. Similarly, you have to follow the procedure for other readings also. Now, what is the first parameter? That is average temperature. Then how to calculate the average temperature? The average temperature is nothing but what you know, that is T2 plus T3 plus T4 divided by 3. You will get the average temperature. But you can see here now the same setup we are using it for natural as well as forced convection. If you are doing forced convection, you have to neglect natural convection. If you are doing natural convection, you have to neglect the forced convection here now. So now I am doing natural convection, so I will neglect this force. That means what? There is fan is off actually. The air is freely moving. Okay, fine. Now I got the T average here. T average is nothing but what? 113.8 degree Celsius. Ti is nothing but ambient temperature that you have taken it here, right? That you have taken it, that is 35.9. Substitute and you will get the Ta here now. See here, Ta you got, T average you got. Thereafter, what you have to do, you have to calculate the film temperature. What is film temperature? That is Tf is equal to T average plus Ta divided by 2. Okay, so now what is T average? Already you calculated. Substitute here. What is Ta? Already you know here. Then substitute and you will get the film temperature as 74.86 degree Celsius. Then you can round off it as 75 degree Celsius. That T5 is equal to Tf is equal to 75 degree Celsius. Then you have to take the air properties at a temperature of 75 degrees Celsius from the data handbook. You can open your data handbook of phase number 34. You can see here now phase number 34. You can refer data handbook CP Kodandaraman and Subramanya. You can open phase number 34 and you can open page number 34. Here is the page number 34 at 75 degrees Celsius. 60 plus 70 divided by 2, you will get 75 degrees Celsius. You will get some properties of the air here now. That properties of air I have written it here. That is density of the air at film temperature, that is 75 degrees Celsius, is 1.0145 kg per meter cube. Kinematic viscosity, you can see now, kinematic viscosity at temperature 75 degrees Celsius is 20.55 into 10 to the power of minus 6 meter square per second. Prandtl number also you can get it here. Prandtl number at particular temperature. Prandtl number at particular temperature, I got it here 0.693. Then thermal conductivity of the air. Thermal conductivity of the air is here. You can see thermal conductivity of the air at particular 75 degrees Celsius. I have noted here now. That is 0.030 watt per meter Kelvin. Okay. After this, you have to calculate the Grassup number. What is Grassup number? You can open page number 112 from your data handbook. So you will get the equation for the Grassup number. Where I can get it here? You can see here now. This is what? This is a phase number. You can see. This is the phase number 112. You can get the Grassup number equation. So I have written that equation. Then what I will do? I will try to substitute the values what required. Okay, so G is constant, that is 9.81, whereas beta is nothing but what? Already we know that beta is equal to 1 divided by Tf plus 273. Then Tf already we calculated here 75. Substitute, that is 75. Then you will get beta is equal to 2.873 into 10 to the power of minus 3. Okay, next delta T. Delta T is nothing but what? Change in temperature. What is the change in temperature? That is T average minus Ta. That is 113.8 minus 35.9 degrees Celsius. Okay, fine. That I have substituted here. 113.8 minus 35.9 into D. D is the diameter of the pipe, diameter of the pin, that already we know, that is 20 mm. So convert that 20 mm into meter. Okay, then what will happen? Now kinematic viscosity. Kinematic viscosity of air is already you have taken here now. Now substitute G as a 9.81, beta is a 2.87 into 10 to the power of minus 3. Delta T is 113.8 minus 35.9 into diameter of the pipe, that is 20 into 10 to the power of minus 3 divided by kinematic viscosity. Then substitute, you will get the Grassup number as 4159.86. 4159.86 is the Grassup number. Thereafter, you have to calculate the Nusselt number now. You have to calculate the Nusselt number. You can get this Nusselt number from page number 138. 138. Where is the 138? You can see in a page number 138, you will get in a Nusselt number equation. That Nusselt number equation you can refer, and you can refer that phase number 138 and you can take the Nusselt number equation from there. Okay, now Nusselt number equation, that is Nu is equal to C into GR PR to the power of what? M. What is GR? GR is nothing but what here now? Grassup number. Where PR is Prandtl number. Then C and M are the unknowns here now. How to get the C and M value? You can see here now. From the data handbook, you can get the value. Multiply GR into PR, you will get the range in between 10 to the power of 2 to the 10 to the power of 4. I got 10 to the power of 3. That is nothing but what? It lies at this particular range. That is 10 to the power of 2 to the 10 to the power of 4. Where the C value is 0.85, M value is 0.188. The same value I have taken for my calculations here now. C I have taken it as a 0.85, M I have taken it as a 0.188. Okay. After this, what you do? You know all the values, right? C, GR, PR and M. Substitute, you will get the Nusselt number. So 0.85 into 4159.86 into 0.693 into the power of what? M is 0.188. Then we will get Nusselt number as, actually it is 3.80. Correction, it is not, it is here 3.80. Okay, once you got the Nusselt number, then what you have to do, you can calculate the convective heat transfer coefficient by theoretical method. How it is? Then we know it already, right? So Nu is equal to K into Nu into K A divided by D. What is Nu? Nu already calculated, that is 3.80. Substitute into 0.03, that is thermal conductivity of air, already you have taken it here, right? Then D is the diameter of the pipe. Substitute, you will get convective heat transfer coefficient, that is small h is equal to 5.7 watt per meter square Kelvin. Okay, next, perimeter of the pipe. What is the perimeter of the pipe? We know the formula, that is P is equal to pi D. Okay, D is again 20 mm, that is you can convert it into meter, that is 0.02. Multiply, you will get 0.0628 meter as the perimeter. Okay, thereafter you have to calculate the cross sectional area of the pin here. What is the formula for cross sectional area of the pin? We know already, that is capital A is equal to 5 by 4 into D square. Okay, 5 by 4 into D square, where D is nothing but what? Diameter of the pipe. Again substitute, you will get the cross sectional area for the pin is A is equal to 3.1416 into 10 to the power of minus 4 meter square. Now thereafter you have to calculate the value of M here. Now what is the equation? M is equal to square root of HP divided by Kf, K suffix F, that is thermal conductivity of the given pin, into cross sectional area. So now here, what is the, now I will substitute the value. H already I have calculated here, that is 5.7. Next P already I have calculated here, 0.0628. Then Kf is nothing but what? Thermal conductivity of the given pin. Our given pin is aluminum here. Then thermal conductivity of the aluminum from the data handbook you can take, that is 204 into area is area is already calculated here, 3.1416 into 10 to the power of minus 4. Substitute, you will get M as 2.363. Okay, then you have to calculate the heat transfer through pin. Okay, how to calculate heat transfer through pin? We have an equation, that is Q with pin, that is heat transfer with pin is equal to K into A into M into delta T into tan hyperbolic ML. It is small l, small m, you have to make correct. Okay, this is small m into L. So now what is K? Thermal conductivity of the aluminium pin, that is 204. That is 204. Then A is already calculated, that is cross sectional area, that is 3.116 into 10 to the power of minus 4. Then delta T, then M is 2.363 into delta T, as I told you already, that is 113.5 minus 35.9. Okay, then tan hyperbolic, what is M? M is nothing but what? That is 2.363. Just to make it correct, here it is a 2.363 into, what is the length of the pin? Length of the pin is 120 mm, that is 0.12 meter. Substitute, you will get heat transfer with pin is 3.25 watt. 3.25 watt. Now once you know the value of heat transfer with pin, now you know the value of heat transfer with pin. Okay, similarly we can calculate heat transfer without pin, that is Q without pin is equal to H into A into M into delta T. H is nothing but what? Already I told you, that is 5.7. H is 5.7. Then A is cross sectional area, that is this much, and M you have to substitute here. I am missing M here, that is 3.63. Okay, substitute, and delta T is again 113.8 minus 35.9. You will get Q without pin as 0.139 watt. Once you know the value of heat transfer with pin, heat transfer without pin, then you can easily find out effectiveness, because effectiveness is the ratio of heat transfer with pin divided by heat transfer without pin. Okay, it is equal to heat transfer with pin is 3.25, heat transfer without pin is 0.139. Substitute, you will get effectiveness as 23.38%. Similarly, I can calculate the efficiency also. How to calculate the efficiency? We have a formula, that is efficiency is equal to tan hyperbolic ML divided by small m L. That is equal to tan hyperbolic M already we know, that is 2.363 into 0.12, that is the length of the pin, divided by M again 2.363 into 0.12. So when we are going to substitute, you will get 0.97 as the value. That is nothing but what? Efficiency of the fin. Thereafter we can calculate the temperature distribution along fin. So what it means actually, that means if I want to calculate temperature at this particular point, the test length of the pin is 120 mm. If I want to calculate the temperature at this particular point, that is the center point, you can consider. If I want to calculate the temperature at this particular point, that is T3. Okay, then what will be the temperature at this particular point? That is half. Is it right? At the center, that means what? 120 divided by 2, that is 60 mm. Then 60 by 1000, you will get 0.06 here now. That is the length is 0.06. Okay. Now I will try to calculate the temperature at location at center of the metal fin. Okay. Then how to calculate? We have an equation, that is Tx minus T1 divided by T1 minus T6 is equal to cos hyperbolic ml minus x divided by cos hyperbolic ml. Is it right? So what I will do here now, because according to my sketch, I need to calculate T3 value. T3 is at exactly at the center of the fin, right? So I will write it here now. T3 minus, because unknown temperatures we have to note down here now. T3 minus TA, that is ambient temperature. T1 represents ambient temperature. Then T2, that is T2. You can take it here. You can take it here now. T2 minus again TA. Minus TA, that is equal to cos hyperbolic m L minus x. Okay, so here I will substitute all the values in this equation. T3 minus TA divided by T2 minus TA, that is equal to cos hyperbolic m, L's total length, capital L represents total length of the fin, minus x. At what distance you want? I want temperature at 0.06 meter. Then substitute, you will get the temperature. Now you already know TA. Is it right? From tabular column, you already know TA. You already know T2. Substitute, you will get the temperature at particular point 3, that is T3. That is, substitute all the values, you will get temperature at T3 is equal to 121.55 degree Celsius. This is what temperature at center of the fin actually. Thereafter you have to write the result. What is the result? We have calculated effectiveness and efficiency of the fin. We got efficiency of the fin is 97% and effectiveness is 23.38%, and temperature distribution at the center is, that is T3 is equal to 121.55 degrees Celsius. Thereafter you have to draw the temperature versus length of the pin. Vertically you have to take the temperature and horizontally you have to take the length of the pin, and you draw the graph for all the readings. At least you have to take 4 readings and draw the graph, and you will plot the graph according to the instruction. Okay, this complete